We've talked a lot about our sinusoidal equations in general. Now let's look to see how they might be used as a practical application. So if we're talking height in meters of a Ferris wheel, let's just do a little sketch here. If we had a Ferris wheel, something like that, right? And you can see how it sort of even looks like our trigonometry from the last unit on a Cartesian plane there. We can also think of this as a sinusoidal graph. And the reason this can be is when the person gets on the ride, they go all the way to the top of the Ferris wheel, they come back down near the ground, they go back up to the top of the Ferris wheel, and so on and so forth until they've done enough revolutions that they get off the ride. So that's a rough sketch of what we are talking about in this problem. Height, they tell us, is in meters and time is in seconds. So that sort of helps us to just identify our y-axis is in meters and our x-axis is in seconds. So we've just done a sketch to see what's going on in the problem. Now let's start to identify some of these answers to our questions that are here. So it asks us, what is the axis of the curve? And from the equation we know the axis of the curve is the exact same thing as q. So we know that y is equal to 11. So in the middle of our graph, it happens at 11. Now as far as the Ferris wheel occurs, it's in the middle as well, and that happens at 11 meters. So what does this tell us about the Ferris wheel, not the sinusoidal graph? Well, it looks like it's the pivot point. It's the axis of the Ferris wheel where all the spokes come off of. So it's the axis as well of the wheel, the axes of the wheel are also the middle point of the wheel you could think of. What is the maximum height? Well, if we know amplitude is 10, so let's just make some notes here. Our amplitude is 10, and our equation of the curve happens at 11. 10 plus 11 is 21. So our max height must happen at 21 meters. And let's look here. So if our height here is 11 and our amplitude is 10 units up, that's how we came up with our 21. Same here, the middle of the ride is 11 and one arm up or amplitude down are both 10 meters. So our minimum height works much the same way. Our amplitude is 10 units, the middle is 11, but this time we must subtract. So our lowest point must be 1 meter off the ground. And that makes sense because when you're on a Ferris wheel and you're spinning around and around, they're not going to have the wheel touching the ground. There's always going to be some distance here so that there's no injury. So as we've already identified, our amplitude is 10 meters, and we could tell that from our equation, our A value in the equation. And what does this tell us about the Ferris wheel? The Ferris wheel itself, it tells us from the middle to the highest point, from the middle to the lowest point. It also tells us if you were actually seated there, let's just pretend this is a seat, you sitting there going around and around on the ride, from the spoke out, you are 10 meters away from the middle. What is the period? What is the amplitude? And what does this tell us all about the wheel? So the amplitude we've already covered, so we actually don't need that question in there again. The period itself is how long it takes to do one revolution of 360 degrees. So that's what we're looking for, the length of one cycle. That's the definition of period. So in order for us to be able to find that, we can take 360 divided by k. So the period is 180. Okay, just excuse me, I just need to go back here. It's not 180. 360 divided by 20, just get the eraser here, is 18, not 180. So if we think of that on our graph, that's how long it takes to do one full cycle of 360 degrees on the wheel. So it takes 18 seconds excuse me, for a wheel to do one full revolution. So what does this tell us about how fast is the Ferris wheel turning? Remember, we think degrees and seconds. So it takes us 18 seconds to go around 360 degrees. So our speed must be 20 degrees for every 1 second. So the seat that you're sitting on is moving 20 degrees from the axes every second. So now that we have all of this information, we can finalize and answer questions like, where are you? How high are you off the ground after 5 seconds? So the equation was 10 sine 20t. So we know now that we're looking for 5 seconds, so we can just substitute that in, plus 11. And then you can use your calculator at this point to solve for your final answer. Be sure that you do your multiplication first and your addition last. It's important with these videos that you do take the time, pause it, and actually use your calculator to be sure that you're getting the same answer that I am. So f at 5 seconds is what we're solving for, would be 20.8 meters off the ground. Here is the next problem that we're going to do. We have a Ferris wheel with a radius of 5 meters. So when we see that the radius is 5 meters, let's just do a little sketch here. So radius of 5 meters, what we recognize even from that last problem, that radius must be the same thing as amplitude. So that helps us right there to start to get organized. We already know what the amplitude is. Amplitude equals 5. And a center at 7 meters. So a center at 7 meters from that last question, we know is our equation of the curve. So we already have A and Q. It rotates at 15 degrees per second, so that will help us find K if we take 360 and divide it by 15. So right away as you start to read it, you can also start to extract some of the information you need. A certain seat begins the ride at the very bottom, so at the lowest point. Determine the equation that models the height of the seat. So a sketch may help us here. Let's just sort of go through here. You'll have graph paper and a ruler. That will make this a whole lot easier for you. I'm going to bring my y equation over here because we're not going to worry so much about negative time. So I have an equation of a curve at 7. 1, 2, 3, 4, 5, 6, 7. So that's my equation of the curve. An amplitude of 5. Let me erase that equation of the curve for a second. And you may want, find yourself doing this as well. I realized that that was too high, so I'm not going to have that line there. Because again, I don't need to worry about negative height, so I'm going to drop everything so this represents a little bit better. So I'm going to do it like this. Because I'm not so much worried about what happens below the line. So again, I have an equation of curve at 7. 1, 2, 3, 4, 5, 6, 7. Dot that in. And my amplitude is 5 above and 5 below. So I know 7, 8, 9, 10, 11, 12. So that's going to be my highest point there. And my lowest point at 2. Now the rider gets on at the very bottom. So I know here's my starting spot of my graph. So my rider is going to go up, down, back towards the ground, and keep riding until he is told he has to get off. So that'll continue on forever and ever out that way. And I know here that one cycle, that this point here at the lowest is 24. That's how long it takes to do one revolution. So it's going to take 24 seconds to go around once. So now let's see whether from our sketch and the information we've extracted, we can actually write an equation. Because I've seen this sketch, I know that I'm going to want to use cos, because I have one perfect cycle represented like this, as opposed to a sign that isn't visible there as well. So I know that my A is going to be negative because this has the U shape, so to speak, upside down. So I have -5 cos, my K is 24. There was no phase shift at all. This didn't move off the x-axis, so I have 24 theta because my P is 0 plus 7. And there you have a complete equation done for another word problem. Our last example for today, and then we'll do more of these practice questions in class tomorrow, which you can see is listed under the graph here on page 398 if you were looking to get a head start. All right, we're going to put in an axis here. Let's just sort of draw one in. You know, you want to follow along at home. You probably want to be doing this work as you can on graph paper, trying some of the questions out. Of course, you'll have a ruler, which isn't going to make everything much neater in your book. So what we have is we're talking about high tide, so the highest point being at 11, and low tide, our lowest point being at 5. It says that the high tide is at 6 a.m. and the low tide is at 6 p.m. So I know that there are 12 hours in between those 2 points. If I need to show 2 full cycles, then I'm looking at about 48 hours in order to represent it, and I'll show. When we sketch on the graph, everything becomes easier to see. So 1, 2, 3, 4, that's our low point there. 6, 7, 8, 9, 10, and that's our high point there. So our highest point starts here. 12 hours later, it's going to be at its lowest point. So I'm going to count by 4 on my x-axis so that I can ensure that I'm going to fit it all in. So 4, 8. So at 12 hours later, I'm at my lowest point. So I've got a point there for my high, my low. Another 12 hours later, 24, then it would be back up at its high point. And it just keeps revolving like this. 36, it would be at its low point. 48 hours later, it's at another high point. So I'm just going to connect these to show you the sinusoidal representation of the tide. So it would look like this. So as far as sine graphs go, I have 2 full revolutions here. So you can see 1, as far as our cos graphs, I have 2 full revolutions there. If you wanted to think about this, I'm just going to take a second to show you how we could also represent this by sine, even though the cos is easier. So those were our points here. If you put in your equation of the curve, that's 11 and that's 5, which equals 16. So that means our equation of the curve happens at 8. Right in the middle there, that's on that line there. So a sine graph can be seen on this graph. You always start where it touches at the equation of the curve and follow it through until it comes back to the equation of the curve. So that's a full sine representation there. But it's in the middle, and now I would have to start to deal with phase shifts. So I much prefer to think of this as a cos graph because I have my 2 cycles there, and I don't have to worry about a phase shift because the coast graph is still right on the equation of the curve. So I'm just going to get myself organized. My amplitude from the equation of the curve to the trough is 3 units. My graph starts, it opens up, so it's positive. I have no phase shift, as I said. My equation of the curve happened at 8 units. So now I just have to figure out my K value. 360 degrees divided by 24. Which is equal to 15. So I now have enough information that I can substitute into cos. A is 3, cos K is 15, brackets, theta, oh there's no phase shift, so that's nice and easy. Close it all up, plus 8. 1 plus too many in there. There we have it. Another equation done from a word problem. We will begin this homework tomorrow in class.